Now we're going to show how the verification done by SAW is integrated into the s2n development process. When a user goes to s2n's GitHub page, they are presented with a build passing badge. This indicates that the code builds, the regression tests passed, and also that all of the SAW HMAC proofs succeed against the current version of the code. Clicking on this badge takes us to the Travis CI page for s2n, where we can see the results of these checks, which occur every time there is a push to the s2n Git repo. This is the log from the Travis checks and shows the result of a SAW run. We can see that we're verifying the HMAC algorithm with SHA-256, a key size of 64, and message size of 1. Each individual verification checks that the code returns the correct result for any possible message and key of the given sizes. It then returns a JSON output that contains statistics such as the proof time and complexity. We then scrape these automatically and generate graphs summarizing the checks that were run as well as information about each function that was analyzed. For demo purposes, we've created our own Travis instance that does a single run of the SAW HMAC checks so that we can quickly see the change in output as we make changes to the code. We're going to show how SAW integrates into the development workflow, accepting correct changes and flagging any errors that are introduced. We'll focus on the s2n HMAC update function, which you can see here. One interesting thing about this function is that it involves a rather strange constant. The comment above explains that this constant was introduced to protect against a timing attack and should have no effect on the mathematical result. If that's true, we should be able to remove this constant completely. We'll do that, save the file, and push the update to Git. As soon as we do the push, Travis will run all the SAW proofs again, and because of the proof automation incorporated into SAW, the new code will pass without the programmer explicitly updating the proof itself. This is important as it lets the proof checking operate in a very similar manner to compilation and testing from a workflow perspective. So Travis has already started the new build. It compiles the code, executes SAW, and produces this green text which indicates that SAW has succeeded in showing that the code is a correct implementation of HMAC for the given message and key sizes. So now we'll look at what happens if we make a mistake. What we'll do is increase this constant by 1. This breaks the correctness condition that the constant should be 0 mod all the HMAC block sizes. So we've just pushed that change, and now we'll go back to Travis to see what happens. In this case, when SAW finishes, it generates some red text indicating that the proof failed, and SAW has also generated a counterexample, which is a set of inputs that show a case where the code fails to give the correct result. This can be turned into a test case that can be passed to the developers to help them debug the code. Here we're looking at the details of the SAW output, but on the GitHub page this would be summarized as a red badge indicating that one of the code checks has failed for the given commit. Now in this demo, Travis was triggered by the code pushes we did, but it also runs on every pull request, so developers can see feedback from the SAW tool as they're deciding whether to merge contributed changes. This acts as a very strong check on the quality of submitted code, augmenting manual code review and providing developers with a high degree of assurance about the correctness of code changes without requiring any extra effort on their part.